Hello, my name is Emma Warren, and today I will be presenting my lab on magnetic braking with Faraday's law. The purpose of this lab is to observe the behavior of a magnetic field which exerts a force on the source of the external magnetic field by collecting experimental data and predicting outcomes with the same variables through a computational model through GlowScript. My predicted results were 1.99 seconds through observed average, and my computational results were 1.736 seconds from the GlowScript. It is apparent that these numbers are very close. The first important concept is Faraday's law. This rule describes how a changing magnetic field can create a current within the conductor. In relation to this experiment, the falling magnet changes the magnetic field within the tube and thus generates a current within the metal tube, in this case the aluminum foil. The next important equation is once again the Biot-Savart law. This law describes the magnetic field created by an electric current. In relation to this experiment, the current within the conductor emits its own magnetic field as described by the Biot-Savart law. The interaction between this generated magnetic field and the magnet's field itself is what causes the braking and slower descent of the magnet. The last equation is once again Ohm's law. This is important to the experiment as it numerically explains that the braking force is lessened in high resistance materials and more so in low resistance materials. Now let's discuss the experiment and my setup. My system was the magnet and the surroundings was the aluminum foil tube. My assumptions included that the only active forces are the force of gravity and force produced by the magnetic field of the aluminum foil tube. For my procedure, I had an assistant record a video to get the timings from later. I then held the tube in one hand and the magnet in the other and dropped the magnet through the tube. I repeated this 5 times. I then took the recordings, slowed them down, and noted the exact time the magnet spent within the rod for each trial. I found the average time spent within the tube to be 1.99 seconds. To answer the checkpoint question, the magnet slows down in comparison to a magnet falling in free space. The speed at which it does so within the tube is much slower, which can be seen when the magnet exits the tube and returns to expected falling behavior. Next, I set off to replicate this experiment within a computational simulation to see if the results were similar. I did this through GlowScript, where each step can be seen in the slide. I first listed my initial conditions for the tube and magnet. I then created a function to calculate the magnetic field of the bar magnet. Next, I created a function to calculate the magnetic flux and followed that by calculating the gravitational force on the magnet from Earth. Then I computed the typical B field at each ring, calculated the total net force on the magnet, and finally updated the magnet's velocity and position through the use of Newton's second law. A graph of the results of my computational model can be seen in this slide. The results concluded that the time in the tube was 1.736 seconds, which was very close to my observed average. Let's move on to the discussion portion of the lab. What if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of the falling magnet change? Well, we discussed earlier that the lower the resistance of the conductor, the greater the magnitude of the braking force. Therefore, if the resistivity of the conductor were reduced as close as possible to 0, the magnet's fall would fall dramatically slower, and in a perfect environment, the magnet would float and not fall. Next, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would cause the eddy currents created by the conductor to be interrupted and therefore their magnitudes to dwindle or cease altogether depending on the size and positioning of the holes as it disrupts the shape of the cylinder. Therefore, the braking effect decreases and the magnet proceeds to fall faster. Finally, why can't we use a ferrous tube like a steel pipe? Well, an aluminum foil tube is perfect because while it is a conductor, its magneticity is lower than a lot of the other metals. Steel, for example, is highly magnetic, meaning the magnet will essentially just stick to the pipe instead of following, changing the magnetic field and generating eddy currents from the tube. In conclusion, in this lab we discussed Faraday's law, Biot-Savart law, Ohm's law, and the effects of changing magnetic fields in regard to eddy currents, conductors, and falling magnets. I hope you were able to learn something along the way. Thank you for listening.